Okay, so this is kind of a bit of a tedious set of notes, but I think we should be able to make some sense of this online. So what we're dealing with here are conic sections. So you may have briefly have touched on these in Algebra 2. There are things like circles, hyperbolas, parabolas, and ellipses. Every one of these can be fit to this general equation. So if I have an ax squared plus bxy plus cy squared plus dx plus ey plus f is equal to 0. So it's kind of like two quadratics stuck together, but with this cross term of xy. Any equation like that is going to give me a conic section. And in the notes, I have the standard forms for a circle. Okay, so the circle, an ellipse, a hyperbola, and a parabola. I'm not going to walk through those in the video. I'm going to let you kind of take some time to meander through that. But I'm going to work through an example. So let's say my example is 5x squared minus 6xy plus 5y squared plus 14 radical 2 x minus 2 radical 2 y plus 18 is equal to 0. Okay, so I'm actually going to bring up a figure from the notes so that you can see what the graph of this actually looks like. Okay, so this is the graph, okay? And you can see that this is clearly an ellipse, as alluded to that this would be a conic section, and this is an ellipse. But unlike an ellipse that's where the major and minor axis are perpendicular to the x and y axis, this thing is on some sort of oblique, and it makes it difficult to see, like, where is the what's the length of the major axis, what's the length of the minor axis, where exactly is the center of this thing. So what we do is we use the idea of a change of basis in order to actually rotate this thing so that it is in a place where we can do better analysis. So the key here is actually finding the correct angle of rotation. So we're going to do a rotation that actually solves this equation. The cotangent of 2 theta is equal to a minus c over b. Now I'm going to leave that without proof. You can do some diving in as to see why that is. But in this case, it's actually going to be pretty simple because that's going to be 5 minus 5 over negative 6, which works out to be 0. So the cotangent is equal to 0. Well, that's when the tangent is undefined. So that's going to be 2 theta has to be pi over 2. And theta then is pi over 4. Okay, so that's how that guy kind of works out. Now, there is kind of a routine here. What we want to do is we have this situation where our guy currently, we want to envision it not being in the standard basis. So this is the standard basis where we have 1, 0, and 0, 1. But we actually want to imagine that it's in some rotated basis. Okay, so like we want to imagine, since the ellipse was down here, that our basis is actually this way. Okay, and that basis can be described using this angle of rotation. Okay, so let's go ahead and do that. Okay, so we want to imagine this thing being in some other basis. So the standard basis here is 1, 0, 0, 1, but the basis that we're imagining this in is going to be cosine theta negative sine theta, and then we're going to get sine theta cosine theta. Okay, and you could check that this is actually a basis. It takes a little bit of work, but again, it will work and it will be a basis for all theta. All right, so what we're going to do is we're going to try to say, if I had transformed my matrix, right? So I need basically I need a transformation matrix that will transform current location into standard basis. So what I'm going to do here is I'm going to say, I'm going to put cosine theta negative sine theta, and then we're going to have this as sine theta cosine theta. Okay, so what we want to be able to do is to take that matrix, cosine theta negative sine theta, sine theta cosine theta, times the current location, which is x prime y prime, and get back x, y, the standard basis. Okay, the location in the standard basis. So this is, whoops, my change of basis that gets me there. Okay, so what I'm going to do here is I'm going to solve this system of equations. I'm going to write out this system of equations. If I write this system of equations out, I get x is row versus column, so that's going to be x prime cosine theta minus y prime sine theta, and row versus column here is y is x prime sine theta plus y prime cosine theta. Okay, now recall in our example theta is pi over 4. So that means sine theta is root 2 over 2, and cosine theta is also root 2 over 2. So I'm going to clear some of this out just to get some room to think up here. Okay, so let's see what this actually becomes, right? So this, using this system here and these realities, then x is x prime root 2 over 2 minus y prime root 2 over 2, and y is x prime. So this means that x is root 2 over 2 times x prime minus y prime. And y is x prime root 2 over 2 plus y prime root 2 over 2, which means y is root 2 over 2 x prime plus y prime. Okay, so that's some kind of fancy footwork there. If you substitute this into the original equation, 5x squared minus 6xy plus 5y squared plus 14 radical 2x minus 2 radical 2y plus 18 is 0. What this is actually going to work out to be is x prime squared plus 4y prime squared plus 6x prime minus 8y prime plus 9 is equal to 0. Now, I'm not going to do all that working out of the algebra there. If you want to verify that one, you can. It'll be a good exercise in algebraic manipulation. But the reason why we like this is that that nasty cross term with the xy is now gone, okay? And this can be reduced by completing the square to x prime plus 3 squared over 2 squared plus y prime minus 1 squared over 1 squared, squared over 1 squared is equal to 1. Okay, so let's think about what's happening here and kind of work this out. This is now, if you look back in the notes, an ellipse in standard form, right? So what do I know about this ellipse? Well, I know that its center in the standard form is at -3, 1. Its major axis is a length of, well, 2 double 2 is 4, right? The minor axis has a length of 1 plus 1 is 2. The apogee, the distance, the maximum distance from the center is 2. The perigee, its minimum distance from the center is 1. I know a lot of information about this ellipse. The only problem is where the ellipse is located. So if I graph this ellipse, that's what it looks like, okay? It's no longer, it's the same exact ellipse, it's just been rotated pi over 4 radians clockwise. So that made it nice so that it's perpendicular to both the x and y axis, and now I can glean all the data from it. And nothing's going to change as far as the length of the major axis, the length of the minor axis, the perigee, and the apogee, but the center's not in the right place. So how do we get back the center? Okay, so here's what happened. In order to do this rotation, I took the points through this matrix, cosine theta, negative sine theta, sine theta, cosine theta. Okay, and I took this x pi, y pi, and got that to the x, y, the standard basis. So now I know that in the standard basis, my center is at -3, 1. So I want this to go backwards. So if I take that same matrix and its inverse times the standard basis notation, I should get back the original basis understanding of this. Okay, so when I look at this, nice for me, these all work out to be √2 over 2. So I'm going to take √2 over 2, √2 over 2, negative √2 over 2, √2 over 2, inverse times -3, 1. And I worked this out earlier using MATLAB, and that happens to work out to -√2 over 2√2. So that's actually the center of this ellipse in its original position at -√2 to √2. So by just simply tracking the rotation using a matrix, I can undo the rotation by taking the inverse of that matrix. All right, so we're going to look at this more in class. I know this is a bit of a convoluted and complicated idea, but it is one of these applications of bases, and it makes calculations a little bit easier. So there you have it. This is conic sections and rotations.